Grade 12, welcome back. Today we will be doing the second session 2017 for the GS students. It's the capacitor chapter. Of course, I would say that LS can benefit from that too, but since they don't have it in the official exam, you're simply stuck with this chapter alone. Now, for this exercise, it's the same formula, same concept, same everything, just different type of questions and like indirect way of asking things. So don't overthink your answers. You know everything. You know every formula. Just try to analyze a little bit more. Okay? So in this exercise, we have document 1, we have a battery E, we have K, the switch, we have a resistor R, and we have a component D that we don't know anything about yet. But since it's the capacitor exercise, then of course D should be a capacitor. Now, in part 1, our job is to identify this component. And we have a resistor R. We have a DC generator of EMF E. There's no internal resistance. A voltmeter, as I said, resistor, and the component D. Now, as we see the table, at the time T0 equals 0, UR was max. And I can say the word max because when we just started the experiment, the current was just floating in the circuit. Okay, the whole voltage of the generator will be going to the resistor. Since the capacitor, it progressively charges or accumulates a charge on its plate. So it doesn't get to a certain voltage immediately. It needs some time. Okay, now, obviously also we can see that it's not a linear function. It's not a linear, a straight line. Because if you can see at 0, we have 12, 0.4, 7.28. The numbers are not just really looking like they would give me a straight line. So the whole exercise tells me that D should be a capacitor. Now here, show that using document 2 and 1.1, D is a capacitor. How can we show that? In the questions, in the official exam, they answered that. Where is it? In the official exam, they answered that. They simply just said UD increase with time, UD equals E minus UR. Okay. Now, what I want to say, if you write the sentence as they said, for me, it doesn't seem completely clear because if you say U of the battery, it's equal to U of the resistor plus U of the component D that we don't know anything about. Okay, U of the battery, it's E, it's a constant. U of R, it's Ri, but let me keep it UR for now because I'm talking about the voltages here. Okay, and UD. So E minus UR equal to UD. So, okay, I'm using the law of addition of voltages here. So I can have, let's say, a battery, a resistor, and a lamp. D can be a lamp. What did I prove here? Nothing. So what you have to specify is that you have a constant E that is usually the maximum value because the battery is giving out, so it should have the maximum voltage, and UR is not simply just any voltage. It's the voltage that is progressively decreasing. And because of this word progressively decreasing, this word here, this keyword here tells me that I have something concerning the capacitor because it's the only thing, or no, I don't want to say the only thing. It's the thing where it takes voltage bit by bit every time it charges. Okay? So it's a good thing to write this formula and prove everything from it. For me, I think it's better if we say that UR that we're talking about in the table is RI using Ohm's law. And since UR, it is progressively decreasing, okay, that means also the image of UR, which is I, is also decreasing. And the decrease of the current, mainly, especially in the presence of a generator, it doesn't appear that easily. If you have a generator, the current must be increasing. How is that happening? This happens in the case of the capacitor. Why? Because the capacitor will charge bit by bit progressively till it becomes fully charged. And when it does, it cuts the current. That's why we say the current decreases, because it will be cut at the end when the capacitor is fully charged. So this phenomenon is what proves that we have a capacitor. So let me just express that. In 1.1, how do we prove that D is a capacitor? I simply say UR is decreasing over time using document 2, which is the table. Okay? Now, according to Ohm's law, UR equals RI. So UR is the image of I. And since UR is decreasing, then I should be decreasing. So we simply say, then I should also be decreasing. And this concept occurs in the presence of a capacitor. So D is simply capacitor. This is a good explanation. Sometimes students mess it up. They talk way more than they should have or talk less than they should have. You have to just to not be repetitive and explain what's the meaning behind the formulas, not just write a bunch of letters and not make it clear what's really going on. Now, in 1.2, deduce the value of E. Deduce the value of E, they're talking here about the voltage. Everything that concerns the voltage, let me restate that simply. They want E, and E is the voltage. And in the table, you also have the voltage of R. It's like, indirectly, they're telling you, find E using everything concerning the voltage that you know in the exercise. So using the law of addition of voltages would be a good choice here. So according to the law of addition of voltages, or Kirchhoff's law, as some of you know it, U of the battery, it's giving out to the resistor and the capacitor. I will call it C or D, whatever you want. Okay. Now I have a problem. UR has several values. UB simply U of the battery. We all know it's E because it's ideal. It's not changing. It's a constant. And this battery of voltage E is giving out to the resistance, to the resistor and the capacitor. But these voltages are constantly changing. So how am I supposed to solve? The best thing to solve something in physics is to use one of the extremes, like at the beginning of the experiment or at the end. We prefer the beginning because simply, if you look at document 2, we have T0 equals 0. So I know the beginning. Okay, it's better than the end. I don't know for sure if 3.2 is the end. So we simply say, okay, I'm uniting, let me say, the voltages together so I can know E, but I have a problem, which is I don't know which value to choose for UR and UD, so we choose the time T0 equals 0. So we say at time T0 equals 0 seconds. UR is not simply UR, it's UR max, which is at the table 12 volts. Or let me just not say U max, let me just say 12 for now. Okay. And UD, it's U of the capacitor. Initially, the capacitor wasn't charged. Okay, so it's simply 0. Now we say U of the battery, which is E, it's equal to 12 volts. And that's it. Now, in 1.3, usually they ask you for E, they give you a graph, and you find where the maximum value is on that graph, and you tell me that E is 12. Simply, they're just giving a table here. It's the same. Instead of drawing a graph, we give a table. Now, let you see in 1.3 equals UBF, B the voltage across the capacitor. So we have the voltage of the capacitor. Calculate the ratio UC over E. Okay. Usually they ask this question, it looks like this. This is 1.3. They ask you about before that question, they ask you about the differential equation, the solution, blah blah blah. You will get that the solution is UC equals 1 minus E minus T over tau. And simply find the ratio, it would be UC over E. And you just replace UC by its value. Okay, you will get 1 minus E minus the time over tau. You choose the time they're asking for, like this, like here, they're telling you that the time is 0.8. You replace the time and you replace tau using the figure or what they asked you about on the previous questions, like you know all of the quantities, and you simply find a value for UC over E. This is a common question. Here it's a little bit different because they didn't ask me about the differential equation and the solution before that. Okay, so I have a problem. To face this problem, simply UC over E, I know E, it's a constant. It doesn't mess with me. What messes with me is UC. How can I replace it with a value? Okay, if I want UC and I cannot get it at this time 0.8, but I have U of the battery and I have UR, every time you have at least two voltages of two components out of three in the circuit, keep the law of addition of voltages in your head. Okay, if you know the voltages of everything except one, it's like in math, knowing everything, every quantity you have in your equation, you know everything about them except one unknown, which is X. You replace everything and you find X. Same thing here. Since I don't have solution, I don't have any other choice, UC can be found from the battery and from the resistor. So simply instead of UC, I replace it with E minus UR over the whole Y E minus UR, because U of the battery is giving out to the capacitor and R the resistor. So the capacitor could be replaced with UB. If we take UR to the other side, we can replace UC by UB minus UR equals UC. And UB is simply E. So E minus UR. E we know it, we just found it, it's 12. Minus UR, which UR I'm supposed to choose? Not any UR, they specified the time. It's 0.8, so this was UR is 4.44. So 12 minus 4.44 over 12. Let me just calculate that for a second. So, 12 minus 4.44 divided by 12, you will get 0.63. And I don't know actually why I was trying to solve that on my calculator. Of course, the difference between, or the ratio between the voltage of the capacitor and the maximum voltage of the experiment, it should be in the phase of charge 63%, which is 0.63. And if it was a phase of discharge, it should be 0.37. Okay, so this answer should be common. Now, deduce in 1.4, referring to document 2, the value of the constant tau of the circuit. Deduce using 1.3. And this is what I just said now, by the way. I found the ratio. It's equal to 0.63. It's a very common number. It's not just any number. So if I cross multiply, I will be getting UC equals 0.63 E. Okay, and this part here, it tells me that the voltage of the capacitor is 63% of the maximum value. And this is not just any expression, it's the expression that specifically happens at the time t equals tau. You cannot have 63% unless the time is tau. You don't have any other option. No matter what the voltage is, no matter what the current is, no matter what the capacitor is, 63%, it should happen at the time t equals tau. So, since for t equals 0.8 seconds, UC is equal to 0.63 E, then T equals tau equals 0.8 seconds. if you had another answer for the ratio like 0.74, okay, it's not a specific number, it's a random number. So it's not a special time. But here it's a special time, it's tau because it's 63%. Okay, so this is 1.4 and we found tau, amazing. Now, show that the capacitance of the capacitor is C. Now, let me tell you something. Asking you in 1.4 for tau, then asking you in 1.5 to find the capacitance C, these are not just random questions. They are highly related. How? Tau is equal to RC. And even though you didn't solve the differential equation to get that tau is equal to RC, it's a given, it's a formula. Sometimes you need to use it. Okay, so what is C? It's tau over R, which is tau 0.8 over R. R, it's in the given. There it is. It's 8 times 10 power 5, and the answer should be 10 to the power minus 6 farad or 1 microfarad. And I will keep reminding you that the capacitance should be very small. If it has to be a huge number, it would be in millifarad or something, or maximum 1 farad, but nothing more. Now, this is the first part of the exercise. We found that this is a capacitor, we found its C, we found its tau, we found everything. Now, I want to specify something that if I don't change the capacitor, if I don't take it out from the circuit and put another capacitor, that means C is not changing. C, it's a characteristic of the capacitor. It does not change unless I'm changing the capacitor itself. So this value of C can be used in part 2. Okay, so usage of the capacitor in medicine. When the human heart does not function correctly, the surgery permits to implant in the human body an artificial stimulator called pacemaker, sending artificial electric pulses to the heart. This pacemaker can be modeled by an electric circuit as shown in document 3. This circuit consists of, obviously we have a battery, E prime. It's not the same as E above. We have a new resistor R prime, we have C, and we have the switch K. And this switch K can be put on position 1, which is above, so we can leave out the circuit under at the bottom of the figure. We can leave that out. Now, if I take the switch and I place it on position 2, like this, okay, then I have to avoid this side of the circuit. Okay. Now, an ideal DC generator of EMF E prime, a resistor R prime, we said that. And the same capacitor C, 1 microfarad. They didn't have to tell you that, by the way. You got your answer. And you should know that it's the same capacitor, so it's the same C. And an electronic double switch K. At T0 equals 0, the switch is at position 1. The capacitor is totally charged instantly. Okay. Then the switch is turned automatically to position 2. So we charge the capacitor. Once it's done, we switch it to position 2. Then the capacitor will discharge. And we have to repeat that many times. At an instant T1, the voltage across the capacitor is UC equals 2.08 volts. So this value for UC and this value for C. But this value for the voltage of the capacitor is not at any time, it's at a specific time T1. It's really important to read the given, by the way. Sometimes there is one keyword that some of the students miss. Now for 2.1, establish the differential equation of UC. So they want the differential equation, and it's really just super easy. Just 2 steps that you have to know, and keep reminding yourself of these steps so you don't mess it up. The first step is you write the law of addition of voltage. And it's really just common sense after that. Usually we say U of the battery equals blah blah blah. But since we have here the phase of discharge, so obviously we don't have a battery. So I will be going back to my picture here, and I can see that C and R, if I put K on position 2, and I avoid the battery above, C and R are in parallel. Okay, so when two things are in parallel, simply we say UR equals UC. And in this case, it's better if you say law of increase of voltages now. Okay, why do I write the law of addition of voltages? Because I use the same expression, but instead of saying they are equal, I say U of the capacitor minus UR prime equals to 0. It's like I'm doing Kirchhoff's law. It's the same thing. Okay, so U of the battery, sorry, U of the capacitor is equal to U of R prime. And since they want the differential equation for UC, I have to keep UC. So I have to replace UR prime. I don't, that's the only case. Now, if you remember, I told you that your differential equation should have U or I or UC, but none of these two together. So here I have UC and I, so I have to get rid of I. How can I do that? I go back to my main formulas, which are I equals d plus or minus dq over dt, and q by itself is cuc. If I fit these two formulas together, q here can be replaced by q here. So I will be getting I plus minus d over dt. And instead of this q, I will replace it by its formula, which is cuc. And since c is a constant, I will keep it outside the derivative. The constants don't have to be inside of dt or d over dt. So plus minus c duc over dt. So what is I in my case? It's plus or minus. How can I be sure which one of them is correct? Since we're having a discharge, so we use the negative sign. Okay, we will be getting UC equals R prime, and instead of I, we will be putting minus at the beginning and C DUC over dt. Some students confuse it and they put the minus in between R prime and C. This is incorrect because R prime and C should be multiplied. If you're putting a negative sign in between, you're messing the equation up. Okay? Now, you have to solve in a way so you can get at the end that R prime C DOC over dt plus UC is equal to 0. If you don't get that at the end, or if you don't have all of the positive signs, then you messed up somewhere. Okay, now you have one more step you can do is you divide the whole thing by the coefficient of DUC over dt. Coefficient, I mean what's next to DUC over dt. So we divide by this R prime C to the whole equation. So DUC over dt will be left alone, plus UC, it's divided by R prime C equals to 0. And this is might be the last form they might ask you for a differential equation. Okay, now, the solution is UCA plus BE minus C over tau prime. This question is also super easy. Every time they ask you for the constants A, B, tau prime, or even if they ask only for tau, or if they ask you to verify that this equation is actually a solution for the differential equation, it's the same question, just asked in 3 different tones. Okay, so step 1, you write the solution in front of you. It's A plus BE minus C over tau. Second step, you find its derivative. A will be 0. Now, if you watch my previous video, you can understand what I'm saying. If you don't, I will say it now. You keep them as they are. So B as it is and exponential as it is. Just keep a distance in between. So you can multiply them by what is next to the time. Next to the time, we have the negative sign and we have over tau. You have to write them here. Minus and over tau. And of course, don't leave the numerator empty. It's 1. Okay, then get rid of the parentheses. You would get B times minus 1. It's minus C over tau, E minus C over tau. So you would find the solution, it's a given, and the derivative. If you don't struggle with math, you don't have to show all of the steps like I did. You can just write the derivative as it is. Okay, but don't skip too many steps because it will feel like you're cheating. So So this is the second step. The third step, we replace expression 1 and expression 2 in the differential equation. So 1 and 2 are replaced in the differential equation, which is what? It's E over R prime C equals, I'm sorry, we don't have a bracket here. We have DUC over dt plus UC over R prime C equals 0. Now expression 1 is UC, so this one here should be replaced with this, with its expression. And we have the derivative duc over dt. It also should be replaced with its expression, which is number 2, equation number 2. So instead of duc over dt, look at expression 2. We should replace it with minus b over tau e minus d over tau plus 1 over r prime c. I will keep it on the side. They are constants. And I will replace uc by its value, which is uc, by the way. It's better if you, when you replace something, it's better if you put it between parentheses so we can move step by step. Now, expression 1 is a plus be minus d over tau equals to 0. Now, this is the third step. It's easy for now. Remove the parentheses. If you have to expand, expand. So 1 over r prime c times a, then times b. Now, the last step and the most important one, take everything that has exponential as a common factor together. So this one here has an exponential and this one here. Okay? Take this exponential as a common factor. I will continue here on the left side. Exponential common factor. And I open a big bracket. The first term that I circled, I removed the exponential and took it on a common factor. I will be left out with minus b over tau. So minus b over tau plus the second circle term, we remove e and we will be having b over r prime c. And some people forget the signs before this expression. Be careful. Now we have one thing that is left alone, which is this. So it's plus a over r prime c equals to 0. Now the last step, we all know in math that the exponential can never be 0. But we all know that if we have an expression that is equal to 0, then we're not supposed to have something that is constantly changing. T here is the time, and it's a variable. The time is always changing. And even though the time is changing, we still have an answer equals to 0, so this is kind of not logical. So we have to get rid of the exponential. The exponential itself cannot be crossed out because it's not 0. Okay, again. How can I say that the exponential is 0 and remove it? It's not. So I try to attack its factor, which is the bracket. So minus b over tau plus b over r prime c should do the job and remove the exponential from my equation. Now take each fraction to one side and remove what's common. Then I will be getting 1 over r prime c equals 1 over tau. Switch them. I will be getting tau equals r prime c, and it's always the case. Resistance times the capacitance. Now, I'm not done here. I have one value that is along the whole road, the whole process, which is circuit in blue, A over R prime C. This constant, A over R prime C, it's left alone with the 0 on the other side. So it's equal to 0. So like A should be 0 in this case. So I found tau, I found A, I still have one missing thing. I found A, I found tau, I still have B. So B is the problem. When you solve all of these steps and you still have one unknown, you're left with one choice. And this is the last step you have to do, which is rewrite your expression. UC equals E, it's 0, so we will remove, sorry, A is 0, so we will be removing A. BT minus T over tau. Okay? I'm trying to find B and I cannot. as I said before, use when the time was zero. This is a perfect way of finding things. Okay, because when the time was zero, everything was clear and smooth. So at t0 equals zero, UC was a charge completely, because I remind you that here we are discharging the capacitor. So at the beginning of the experiment, it was fully charged. So you see at the time t0 equals zero, it was fully charged, which is E prime. Let me be specific, E prime. It was just like the battery. Okay, so since you see it's equal to our E prime, and UC is also equal to BE minus the time, but we just said that we're using the time zero. So instead of the time, I will be putting zero. And the exponential of zero, it's one. So simply, I will be getting B equal E prime. This small line here, a lot of students forget it, but it's part of the process so we can find the solution. Then at the end, you say that you see that you gave to us A plus B, P minus C over tau. No, I know it. It's your C equals A, it's zero. B, it's E prime. E minus T over tau, which is R prime C. And I got my solution. You can get around 2 points or 2 points and a half just from these two questions, and they are very repetitive. Like you cannot mess that up. Now, 2.3, determine graphically the value of tau prime. Graphically, the value of tau prime. Okay. Okay. So here, I have the same capacitor, but I have different resistor. Okay. Okay. So I will try to explain something to you. Here we have the maximum value, and the voltage of the capacitor is decreasing because of the phase of discharge. Okay. Then when it reaches to this point, it will be having a boost from the battery again. Okay. And it will be discharging again. Then it will reach a point where it boosts again, then and so on. Okay. So okay. So to find tau graphically, as we said, UC equals, it should be equals to 37% of the maximum value E prime, which is 5.64. How did I suppose that? Because the maximum value we're starting with is 5.64. Okay, so what is UC supposed to be? I suppose it should be 2.08 as they mentioned it in the graph. 0.37 times 5.64. It's yes, 2.0868, but let me just get over with it. So 2.08, it's here. When my voltage was here, where was the time? It was T1. So using the graph, when the voltage is 2.08, T1 is tau. Okay, now how can I get the value of that? Use the scale. You have 1 square, 2 squares, 3 squares, 4 squares, 5 squares. 5 squares, they represent 1 second. 1 second. Okay, but T1 represents 4 squares. So how much should the time be? T1 or tau? 5 over 4 equals 1 over T1. So you should be getting 0.8 after you do that. Okay, you just do like cross multiplication or proportions. 5 over 4 equals 1 over T1. And you got that. Okay, so it should be 0.8. So tau is 0.8 seconds. Now, same repetitive question. 2.4, the value of R prime. They asked you for tau for a reason, but did they give us C? Yes, they gave us C. So simply, we just say that we now know tau. Which question is that? 1.4, 2.4, 2.4. So 2.4, they're asking for R prime. We know that tau is 0.8, and we know that C is 1 microfarad. And we know that tau is equal to R prime C, so R prime is tau of C. So R prime is equal to 0.8 over 1 times 10 power minus 6 to convert it to SI, of course. So we will be getting R prime equals 8 times 10 to the power 5. Yeah, 5. Okay. Please write the units, write the steps. Don't try to look like you're doing the calculations in your head. Write everything you can write. Don't blab. Just write what's need to be written. Now, in part 3, indicate referring to document 4, which is the figure, the value of T1. Okay, we can see that 0.8. We mentioned that before. How do we do that? Using the squares, 5 over 4, 1 over T1. Let me just check the session again. Maybe they used another method, and that's completely fine. This is it. Yep. So graphically, T equals tau prime, yeah, which is 0.8. Then they re-ask the same question. They just wrote the answer. That's fine. So 3.1. 3.1, we simply just say that T1 is equal to 0.8 seconds. Now 3.2. Now for 3.2, deduce the duration separating two successive pulses. What they mean by pulse is not like finding two distances or two, let me say, oscillations. Like that, from here to here, and here, two pulses. No, they mean when you charge the capacitor, then you discharge it. How much time is it taking? This is what they mean. Okay. So in 3.2, the duration delta t is not any time or like time you can get from the graph. Okay. You need the time where the capacitor charges and the time where it discharges, and this is simply the duration for the pulses. Okay. Now, if you remember what they said on the given, they said somewhere that the capacitor charges instantly. There it is. So the time for the charge is approximately 0. It doesn't really count. You know, then when we discharge the capacitor, discharge, when I say discharge, I mean I'm having a maximum point, then I discharge and I will get to the bottom of the curve. So it's from when it was 5.64 to when the voltage became 2.08. So it's the time from here to here, which is T1. I already know that. So it instantly charges 0, plus the discharge is taking 0.8. So delta T is 0.8 seconds. Deduce the number of beats of the heart per 1 minute. When they say 1 minute, they mean 60 seconds, right? And it's logical more than a formula. The number should be 60 divided by 0.8. Because when we're charging and discharging the capacitor, it takes 0.8. How many times we're doing that? How many times we're finding a heartbeat? And how many times we're doing that again and again in 1 minute? So it should be 60 over 0.8, which is 75 heartbeats. Okay. If you're studying by yourself and you're reading the solution and you assume that you can write just like they did, I will assure you that this problem can take you like 2 whole pages to solve, where they just showed you in the session, the solution of the session, here it is, that it's super simple, it's super easy, and you can just write briefly the things. No, if you need to get the full grade, you have to write. Okay, it's not simple as that. And what I want to say is sometimes, like the number of beats, teachers cannot expect that type of questions. Of course, we can solve the problem with you and show you that we have that kind of thing, okay? But we cannot expect what might be asked in an official exam. So you have to be prepared. Don't overthink your answers. Just think logically. Like if I have 1 minute, which is 60 seconds, and one heartbeat, the phase of charge and discharge, it takes 0.8. How many times then can I repeat that in 60 seconds? So it's 60 over 0.8. And try to have an answer that is logical. Like having C that is 5 farad or 50 farad, that's huge. Okay. Having a number of heartbeat in 1 minute less than 75, like 30, let's say, also that's not reality, that's not logical. So from the answers, you can know what's best. Finding the ratio UC over E equals 0.63, that's normal. But if you get 0.75, let's say, that's absolutely wrong, because 0.75, nowhere we mentioned that number and how special it is in the course or anywhere else. Okay, so, and if you write the units correctly, the formulas correctly, you can get a lot of grades. Some people really mess things up because of these. Good luck. If you like the video, subscribe, share, like, comment, support as much as you can. And thank you so much again.